One.
All right, in lesson 391, we want to talk about parameters. This will be a relatively easy lesson. It's really more of the same type of stuff that we've been doing. We're just talking about a new vocabulary word, basically. In order to fully understand how various functions model real-world context, we need to understand how changing parameters will affect the functions. This lesson will explore the effect of changing parameters on linear and exponential. We'll also interpret the effects of changing these parameters in a context. All right. So again, pause the video, read through these key concepts. Again, the reminder, of what a linear function looks like, y equals mx plus b. Parameter of that function is m and b. So it's your slope and your y-intercept. That's the parameters. Changing either one of those will obviously change the way the function looks. For an exponential function, we're used to a times b to the x, and we're going to say that a is just your initial value, and it's really not having that much of an effect. K is going to be some number that's added onto the end, which remember we talked about does a vertical shift of some sort, either up if it's positive, down if it's negative. And then B, which is the rate at which it's increasing. That's the thing you are repeatedly multiplying by. Okay, those would be the two parameters there. So, example 1, you visit your own apple orchard. Pick your own apple orchard, sorry. There's an interest fee of $5 plus you pay 50 cents for each apple you pick. Write a function represent this scenario. Complete a table of values, show your total cost if you pick 10, 20, 30, 40, and 50 apples. Graph the line and identify parameters in this problem. What do the parameters represent in the context of the problem? So let's start with our equation, which would be f of x equals 0.50x plus 5. Okay? Our parameters, as we talked about, are these two things here. We'll come back to that in a minute. So there's our function, our table. We have x and f of x. And we have 10, 20, 30, 40, 50. All right, and that's 5. And if we plug those in, we can see what we get. If we plug in 10, we get 10. If we plug in 20, we should get 15. Okay, if we plug in 30, we should get 20, and so on and so forth. Okay, so then we can plot those points. If we're graphing this, what quadrant will we be limited to, right? So parameters is going to refer to, in some senses, what quadrant it should be in. So if we're counting by tens, 1, 2, 3, 5. 1, 2, 3, 4, 5. So let's say we're counting by tens. And we'll count by tens here too. 10, 20, just so we can hear everything nice and even. All right, so 10, 10. If you plugged in 0, it'd be 5. We didn't do that point, but that's where it would be. 20, 15. 30, 20. Again, you're probably better off doing this, on graph paper. Obviously, I'm not. 40, 25. I'm doing the best I can with what I got. And 50, 30. And we can see pretty clearly that's a linear function. Remember, whatever your x's count up by, you have to keep that pattern. Whatever your y's count up by, you have to keep that pattern. You can't skip numbers. They don't necessarily have to be the same. Like you can do 10s on the bottom. I could have done 5s going up and down. But you got to keep it. You got to keep the rest of it the same. You got to keep the interval the same. So you start counting by 5s, you have to keep counting by 5s. All right, that's the end of example 1. The parameters we talked about were 0.50, which in this context mean what? That's the slope, right? That's 50 cents per apple that you pick. And then $5 is your cost to get in. So if that 5 changed to say $6 or $7 or $8, that would be changing the initial cost to enter the enter the apple orchard. And if the 50 cent changed, that would be changing how much it costs per apple. Maybe they're running a special where it only costs 25 cents per apple. Half off basically per apple. All right, so moving on to example 2. You deposit $100 in a long-term certificate of deposit CD in which your money will double every 7 years. Okay, write a function to show how much money you will have in 7, 14, 21, 28, and 35 years. Use the function to create a table and then graph the function. What do the parameters represent in the context of this problem? So here we go. We have f of x equals, and then my initial amount is 100, and then it's doubling. So I see that word right there. It's telling me it's exponential. Now, how often does it double? It doubles every 7 years. Okay, so it's x divided by 7. A lot of us still aren't understanding that concept. Okay, so in 7 years it'll double 1 time. All right, so we have x and y. We don't have anything added onto it, so I don't have to worry about any of that. So we want to do 7, 14, 21, 28, and 35. All right, so in 7 years it will double once. So that would be 2, that'd be $200. Okay, in 14 years it would double twice, making it $400. And we did 21 years, that'd be 2 to the third, that'd be $800. And we should be able to see the pattern here, 1,600 and then 3,200. Okay, obviously graphing this is going to be a little bit tricky depending on what you're counting by. All right, so I think what we'll do is we'll count by 7s on the bottom. So 0, 7, 14, 21, 28, 35. And then counting up, I think we'll go by 200s. So 200, I probably won't even be able to fit the last one on there, but that's okay. Yep, I'm not going to fit the last one, but that's okay. You'll be able to get the idea. Okay, so I'm counting by 200 doing that. So at 7, we're at 200. And then our initial value again was 100. So we can plot that one as well. 14, we're at 400. 21, we're at 800. 28, we're at 1,600. And like I said, the last one won't even fit. So we get the idea that this is an exponential curve. Okay, parameters in this one are the base, which is 2, and our added amount on the end, which is 0. Okay, so yeah, that's those. Don't worry. I mean, the context here, the rate is the big one. The only parameter we have is the rate, which is double. Okay. All right, last example. You're a growing bacteria in science class. Start with 1, it doubles every 12 hours. Write a function showing bacteria you'll have after 12, 24, 36, 48, 60 hours. So basically, the exact same setup as before. So f of x equals 1, because you started with 1, and it's doubling, and then every 12 hours, so x over 12. So your t-chart here is going to be 12, 24, 36, 48, 60. And then, of course, after 12 hours, it'll double 1 time, which means level 2, and then 4, and then 8, and then 16, and then 32. All right, so the graph, again, we're limited to the first quadrant here. The graph's going to be not so good on this one. That's okay. 12, 24, 36, 48, 60. Again, I can do that because these are all equal intervals. Right, we're going up by 12s here. So that's the reason I can just do this with the points that are there. If the numbers didn't go up evenly, then I wouldn't be able to do this with my number line the way I'm doing it. All right, and then here I think we'll count again by 2s. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Obviously, I'm not going to be able to hit